Falcon 900B, 900EX, 900C have 6 DC tach generators installed, one on each wheel. Hubcap turns the smooth shaft on the front of the tach generator with what they call a sleeve. It's a press fit, and it is very important that all 6 sleeves are tight to get these tach generators to turn at the correct RPM. 3-pin plug on the back. 2 of the pins are used. We'll go into that detail. And here we have a sectioned generator. This is a pie slice style armature that the brushes ride on. So the brushes are axial this way and the armature rolls past this way. The commutator spins, the brushes deposit a black film on the armature, and that buildup of film is one of the things that contributes to resistance between the brushes and the commutator. Typical permanent magnet DC motor here. Permanent magnets on the outside, windings on the inside. Notice there is no moisture seal on the front of the unit here. Water's free to ingress from the hubcap side. These units can be wired backwards and have been wired backwards from the factory. There's 2 little posts here that goes to the brushes, and then pin A and pin C over on the plug. They have been wired backwards in the past, which has led to difficulties on the airplane. So some of the tests we do will be testing for polarity of this unit. There's a troubleshooting worksheet available on www.av-ts.com. We'll go right into troubleshooting the resistance on the little tach transducer. We'll pay careful attention to get the polarity correct on the voltmeter. It will become important as we move along, the polarity that we use on the tach, so on the meter. So we'll make sure we're, for example, red lead plugged into positive, goes to a red lead, goes to a white test lead, whatever, so you can keep your polarity straight. We'll make sure we kind of double check our little polarity on our little tach generator. Here's the large key, okay? And then pin C is off to the side of the large key. Pin A is off to the other side. And it's important that we conserve that polarity right there. Looks like, first of all, we're starting off at about 803, which is a little high. This could be a bad one. On your little troubleshooting worksheet there, you've got a little chart that shows a little log to log in the highest and lowest resistances. So a couple of tricks to this. Let's turn it just a hair and then let go. So there we see a 745, that's upper limit. 744. Now what I'm doing is turning it. There's an 830, so that's out of there. This transducer's generator is a little bit high resistance. Notice I'm moving the transducer a small tenth of a turn or less, then letting go of it, then observing the resistance. Other thing you might do. Tap on that shaft a little bit. This one's not too good. This one's a little bit high resistance right here. So we'd go a tenth of a turn at a time, and we'd log in. Looks like we saw an 8, something in the middle, 830 or 850 there. Now it does not make any sense to, don't worry about the numbers while you're turning the shaft. Of course the meter will just be erratic. So looks like I saw a 711. That might be my lowest one. Ooh, there's a 650, so we're all the way from 650 to middle 800s. There's an 850, so this is a pretty rough one right here. Okay, so I've seen everything from 650 to 850. We can go around on all 6 transducers. We'll carefully go around, log in the highest and the lowest resistances that you observe at every clock position. We'll kind of analyze that here in just a bit. Okay, next we're going to do a little resistance check with an analog meter. Of course, the first thing we're going to do with the analog meter is zero the ohm scale. set to ohms times 1 here, and then 0 the scale so it reads correctly. We'll be sure and preserve our correct polarity here, and do a little resistance check. Same drill. We'll turn it just 1/10 of a turn, and we'll watch. And I'm seeing about 50 or 100 variation here, which is not great. What I'm looking for is one clock position here that is greatly different than every other clock position. And these are all very similar. Next thing we'll do is leave this analog meter on. We'll turn this to volts. And with this tachometer faced towards your face, turn the shaft clockwise, and the meter should read positive voltage, assuming we've got all our polarity right. What you're watching for is this tachometer to be internally wired backwards, and it might look like that, driving the needle back the wrong direction. That would be a transducer wired incorrectly internally. Okay, this time we'll do a voltage check. We'll use a single driver off the AS100 system, Falcon 900 drive adapter, and set up with our pin A and C here. Straight test leads, nothing special there. Fluke meter set to volts, and we'll just go ahead and bring this right up to 1000 RPM. And we can do a quick little voltage check. Looks like we're right close to 1000. And we're right on about 5. We also have the ability, as per the CMM, to use a loaded lead. That's just a 5000 ohm resistor right across the leads. We can go right into A and C. And we can come right up to 1800 RPM here. And it looks like our output is 7.8 something. That puts us right in the middle of the range there. This time we'll use an air drill and a little regulator to drive the motor generator to a fixed RPM to test the voltage. Sample pin A and pin C on the back here. Voltmeter set to volts. We're expecting about 5 volts or so. Piece of flexible weed eater line and a number 30 drill installed backwards in the drill is good enough for an expedient tach driver. And to get our little tachometer to hit, we had to have a little bit of black tape and a little bit of reflective tape there. That'll cause the tachometer to hit a little bit better. So it looks like we're at 890, coming up towards 900. And coming up towards 1000 RPM, and then 4.995. So we're right there close to the acceptable range. Okay.
Thank you for watching this troubleshooting tutorial. It is part 2 of a 4-part series. For more information, please visit av-ts.com and heart-aviation.com. Thank you.